joules over K. Like, can you just get rid of the next formula and move 6.02 times 10 to the 23 onto the left side?
Wait, say that again? I could just, since mole is just a number, all I did was just substitute in for that number.
Yeah. So,
That is legitimate.
yes, I agree.
Okay.
But can you not just make it one equation where it's 8.314 joules over 6.02 times 10 to the 23 times Kelvin?
Yeah.
Okay.
Yep. Other questions? All right, since we're talking about thermodynamics, we're dealing with temperature here. Let's talk about the 3 laws of thermodynamics. Sorry, the 4 laws of thermodynamics. Law number 0. 1, that'd be a silly place to start. Why did they have the 0th law of thermodynamics?
You have to start somewhere.
Yeah, most places start at 1. It's Newton's 3 laws of motion. There's first law, second law, third law. He didn't have a 0th law.
Yeah, because he's advanced. This is the basic.
You're sort of on the right track there. It is, the 0th law is basic, but why did they not call it the first law?
Because they wanted to.
There's another justification for it.
Do the others depend on it to work? Is that what you're about to say?
Yeah, but why would they still not call it the first? All right, we'll leave it as a mystery. All right, so the 0th law. Or 0 LOT. In mathematics, what is the transitive property of equality?
What?
The transitive property of equality in mathematics.
Does this have to do with congruency?
I mean, you could put it in there.
Would it make it more
Congruency, I think, would be a
complicated?
more specific case of it. Pardon?
Would it make it more complicated?
Yes.
Okay.
If A equals B,
Commutative property.
if A equals B and B equals A, that's reflexive property. If A equals B and B equals C,
Oh, and we'll see.
yes, if I heard correctly. So the transitive property of mathematics of equality, transitive property of equality in mathematics. If A equals B and B equals C, then A equals C. That, it's something I think most people are going, yeah, of course. 0th law of thermodynamics is in essence the same thing. So if A is in thermal equilibrium with B, and B is in thermal equilibrium with C, then A is in thermal equilibrium with C. It is not an earth-shattering concept.
Which lines of the 0th law? Is it because it's like, I don't understand why it would be the 0th law.
Instead of the first law,
Yeah.
I was gonna leave that as a mystery. Now, this is not an earth-shattering concept. First, what is thermal equilibrium?
Where, like, so you know when you hold an ice cube and it melts in your hand until it's room temperature?
Yep.
that means that you and the ice cube are, well, melted ice cube are at the same temperature. There's no, well, they're still jumping because the atoms can't just not move, but like it's at a point where it's not changing as significantly anymore.
Alright, so the temperature is basically, the temperature of the two environments is the same, statistically speaking. As Robin said, particles can jump back and forth, and so pretty much for anything thermodynamics, you can always throw in the term statistically speaking, just to be more accurate. So in thermal equilibrium, we have two systems. There's no energy flowing back and forth, statistically speaking.
Zeroth law. Could it possibly be because it's conservation of energy?
That's the first law.
Okay. So then what's the zeroth law?
This is the zeroth law.
Which is?
If A is in thermal equilibrium with B and B is in thermal equilibrium.
There's not a fast name for that?
I kind of like transit property of thermodynamics, but I haven't seen it written down anywhere. All right, so with this in mind, I have a classic mercury thermometer on the wall here. Just imagine. Assuming all of you can have seen a mercury thermometer, but just in case you haven't, you have a tube, a reservoir of mercury in here, enclosed in glass. What does the thermometer measure?
The amount of kinetic energy.
The amount of heat being transferred.
No, and kinetic energy of what?
This is
Of the system, she said.
What system?
I don't know, like the system you're trying to measure.
It's in the room. I have a thermometer sitting in this room.
Oh,
Let's say it says 20 degrees Celsius.
I don't remember. I was told this, but I just, all I know is like a thermometer measures your kinetic energy. Like that is what temperature is. It's measuring the amount of kinetic energy in a system.
As the first part of it.
But I don't understand. Like if it's just measuring the kinetic energy of the system, what's more to it?
You faded there.
What's more to it? If it's not just measuring the kinetic energy in the system.
But you have to, what system is being, what we're finding the average kinetic energy of? We can just say temperature at this point. The temperature of what?
The room.
No. It is not measuring the temperature of the room. What is it actually measuring? The temperature of what?
The surface it's in contact with.
Closer.
Assuming we're excluding radiation.
The wall.
Not the wall,
The air.
not the air.
Are you referring to that one specifically?
Sure.
The whiteboard, perhaps?
The thing that is attached to, so you know how many degrees.
Thing that it's attached, oh, you mean the plastic backing or
Yeah.
whatever it is? No.
Is it?
You're very close though.
Is it the actual thermometer itself?
More specifically, thermometer is, has a lot of parts to it.
The
Which
air
part?
within the
Liquid
thermometer?
on it.
The what?
The air within the thermometer?
Not the air within the thermometer.
Isn't it what is it?
It's like you're doing everything you can except
The
to say the
temperature
right
of the
word.
mercury.
What is it?
The temperature of the mercury.
Yes. The thermometer here is actually measuring the temperature of the mercury.
Were we not referring to what the mercury, oh wait.
Now, why do we say it's the temperature of the room? Well, one, it's a whole lot easier to explain to people. But two, if this is in thermal equilibrium with the glass that surrounds it, and the glass is in thermal equilibrium with the room, then the mercury is in thermal equilibrium with the room. But really what's being measured here is the temperature of the mercury. As energy goes into it, it expands. As energy is taken out of it, it drops. We are trusting it's in thermal equilibrium with the glass. We're trusting it's in thermal equilibrium with the room.
Could you go to the last slide on the blackboard?
So does that mean that the zeroth law is the zeroth law because it's just explaining temperature? Like how we,
It is a fundamental law, but it doesn't answer the question of why it's not the first.
It's just a shot. So heat energy, thermal energy dissipates once it's like potential to kinetic. Once it's kinetic, it dissipates shortly after. So there's like little left. Could that possibly be it?
No, it's a much simpler explanation that the question is not why is this more fundamental. The question is why is it zeroth, not first.
It was invented in BCE.
No, I don't think so.
Okay.
It's possible. I have not checked the Library of Alexandria.
You can't, so.
Yeah.
Could you go back once more?
All right. So the zeroth law, nothing earth-shattering. This first law is also nothing earth-shattering. We've dealt with it before, but we're going to make something that we've done already look far more complicated. If I have a system here with a certain amount of energy in it, which we will call E sub I.
Does that have a reason?
Actually, I make E sub O, so I can use I for N. Pardon?
Does that have a reason that it's just a thing? That it's that letter specifically?
A system's gonna have a certain amount of energy in it. I'm just
Okay.
making the claim, I have a system, it has energy E sub 0. I can put energy in, I can take energy out. So the final amount of energy in the system is whatever I started with, plus whatever I put into it, minus whatever I took out of it. Conservation of energy. You're looking at me like you want to ask something.
No.
Okay. So conservation of energy, first law of thermodynamics. Now, I haven't made it look more complicated yet, so let's do that. When I have energy being transferred from one system to another because of temperature differences, that is what we call heat. So heat is the energy transfer. Heat equals energy transferred because of temperature differences. So this energy in, we can just label as heat. Now, we need some letter because we can't go around writing words out when we can just use a simplified letter here. And so, of course, the symbol for heat is a capital Q, which I think probably originally stood for the quantity of energy.
Wondrous.
So instead of E sub I, I'm going to put Q. Now, energy out, if I have a system here that is getting rid of energy, well, it's doing work. So instead of energy out, I'm just going to label that work. If I subtract the initial amount of energy over, I end up with a change in energy of the system is equal to the heat in minus the work that the system does. It is just conservation of energy dressed up to make thermodynamics people feel special. Now, we're going to take it one step further, because that is just too simple. To me, this makes sense. I have a system here, I have energy in, energy out. Some standards in textbooks, and usually the first part of thermodynamics textbooks establishes which system they're using. The other system is that they look at the environment, and there's this pesky interloper. And so this energy in is actually energy out of the environment, and this is energy into the environment. Yes, that's the right look. So we could write this whole thing also if we look at it from the environment's point of view and not the subsystem here, from the outside point of view. And the fact that the change in energy of the environment is going to be W minus Q.
Could you go forward on the blackboard? Forward slides.
Or,
Blackboard.
sorry, I was old school.
Once more. Okay, thank you.
All right, so first law of thermodynamics, just conservation of energy. It is, again, nothing particularly special. Some textbooks will have an entire chapter on it because they will go into nitty-gritty detail, which I will spare you from. You're welcome. Questions up to here before I get to the depressing one?
Like the second law.
Yes. All right, second law of thermodynamics. I call it the depressing one. There are a couple different forms of it.
What do you call the zeroth law? Transfer?
A transitive property of thermodynamics.
Thank you.
That's what I call it. To LOT. There we go. That's it in a nutshell. We're gonna make it sound more complicated than that, but that's in essence it. We could also look at it as you will spend more energy than energy you can produce. If I take this marker and it falls, it has, it gained kinetic energy, then it lost energy, but I want to put that marker back where it was. I'm going to put potential energy into that marker. So I lift it up and back to where it was. Now the energy that I spent lifting it up is more energy than this actually gained in potential energy. So I've lost energy. It's called exercise. So I've lost energy in order to pick the marker up. So ultimately, if everything is always going to give up energy, we're never going to break even, the environment's always going to get some energy out of the system. All actions lead to the same temperature. Or same kinetic energy. I have a particle here that's sitting along, it gets hit by another one, this will gain energy, the one that hit it will lose energy, and then it'll collide with others, and eventually all these particles will be traveling around at the same speed to the point, or same kinetic energy, to the point where if one hits another one, neither of them go any faster. This is known as heat death of the universe. There's a video by Melody Sheep which I think really nicely illustrates it. Do not do it if you're in a sad mood or a sad mood.
Does she use knives or something?
Pardon?
Does she use knives or something?
I still didn't.
Does she use knives or something?
No. It basically it's Have any of you seen the Power of 10 video by the Eames? This came out in '69, where they start out with a couple on a picnic blanket
No.
and they zoom out. Every second.
Oh, so they keep zooming out and zooming out and zooming out, and there's new details every time.
Yeah, or fewer details, depending on way you want to look at it. But they do keep zooming out until, it gets to the point where the Earth's just a speck, and then the Earth, you can't even see the Earth, and you see the solar system, and
Yeah, I've
they
seen
keep
that.
zooming out. And then they zoom all the way in down until you get to the electron cloud. It's called Powers of 10. In that one, I think every second that passes, you are at a new power of 10. So after 1 second, you're 10 meters above them, and then 100 meters above the next second, and so forth.
Is the purple the first law?
Yes. In the video by Melody Sheep, every second that passes of our time, it's another power of 10 in terms of years. And it ultimately looks at, well, in essence, the death of everything. This is why I call this the depressing one. Now, bundled up in this is a concept called entropy. Entropy is a measure of how things are ordered. So things have a tendency to go to a higher entropy, to a more random.
Does Q equal heat or heat transfer? Does it matter?
Q equals heat. Heat is energy transfer. So entropy is this idea of how things are ordered. The more random it is, the higher the entropy is, and so entropy increases. Statistically speaking. If we want to decrease the energy, it's going to take energy to do that, and we'll lose some in the process. So second law of thermodynamics, labeled the second law of thermodynamics, is actually the third one that we've listed. And now the fourth one to list, or the third law of thermodynamics, because we don't want to make it too simple.
What does the O mean?